So let's see what is a symmetric matrix first, and then we'll look at what is a skew-symmetric matrix. So let's first look at the symmetric matrix. The definition of symmetric matrix says that the transpose of a matrix is the same as the matrix itself. So A equals A transpose. That is, if we interchange the rows and columns of a matrix, it does not change the structure of the matrix. If you are given two matrices, say you have been given A matrix and you've been given A transpose matrix, you won't be able to tell which is the A matrix and which is the A transpose matrix. So let's look at an example. Let's say I have 1, 1, 1, 1 as a given matrix. Now if I transpose this, what will be the transpose of this matrix? The rows become the columns and the columns becomes the row. So the first row essentially is 1, 1 here. So instead of writing it row wise, I write it column wise. So I get 1, 1. Similarly, the second row is also 1, 1. So I write 1, 1 as the column. Now look at these two matrices. Aren't they the same essentially? That is what I essentially mean when I talk about a symmetric matrix. That is, when I transpose the matrix, it does not change the structure of the matrix essentially. The matrix remains the same. This is what we call a symmetric matrix. Another thing is a symmetric matrix is always a square matrix. So why is that so important? Whenever we transpose a matrix, the dimensions of the matrix changes. That is, the m cross n of the original matrix becomes n cross m of the new matrix. Now, for one matrix to be equal to another matrix, all the individual elements of the matrix needs to be same. If you have one particular box of chocolates and you have another second box of chocolate and you want somebody to tell you whether these boxes are same or not, you will have to count the number of chocolates in the boxes. You'll have to look at the wrappers of the chocolates. You have to look at all the individual chocolates in the boxes with all the properties in the chocolates. That is, you have to make sure that everything about those two boxes are identical in nature. So of course, the elements, besides being same, they need to have the same orientation. So if they are in this form, that is a vertical rectangle form, and if this matrix is in a horizontal rectangle form as such, just talking to the orientation, I won't be able to tell that they are of the same nature. So I have to make sure that even after transposing, the shape of the matrix doesn't change. Now, what shape do we have that does not change its orientation if we flip it? Because in this case, we are essentially flipping the matrix this way, right? This matrix becomes this. So the columns become the rows and the rows become the columns. So we flip the matrix this way. So which shape remains the same if we flip it in this way? We have a square which does not flip its which does not change its shape. So essentially, symmetric matrix is a square matrix. Now, obviously, we'll find out later that a skew-symmetric matrix also needs to be a square matrix. But before we do that, we need to find out what is a skew-symmetric matrix. So essentially, a skew-symmetric matrix is a matrix such that when we transpose the matrix, the elements become negative. Now, I won't be using an example right now, but we'll look at an exercise later. And what I want you to do is try to find out an example for another example for symmetric matrix as well for yourself, because skew-symmetric matrix tends to confuse a lot of people because the elements need to become negative of the original matrix. So what we'll do is we'll take a skew-symmetric matrix and we'll try to find out a skew-symmetric matrix or a matrix such that the elements, when the matrix is transposed, the elements essentially alternate in their sign. So the positive becomes negative and the negative becomes positive. It is not necessary that all the elements of the original matrix needs to be positive or then we have the negative elements on this side. We can have negative elements on this side which will become positive. So essentially the signs alternate in direction. What you can do is, this is an easier way of thinking of it. So let's say I have two matrices, and what I want to do is I have to change the nature of the matrix. That is, I have to transpose it such that the elements become opposite in direction. Now look at it this way, this element and in this matrix we have this element, their positions do not change. So one thing we know is these are both square matrices. So we need to find out, let's say, take it in an easier step. Let's say we have to find 4 elements. So such that these elements also we can find out. So based on this element, we can find these elements. We can essentially put a minus over here and then put a transpose. So we just need to find these 4 elements. Now, by the definition of the matrix, this element does not change its position. But we have to put an element here such that we have the negative of that element. 0 is the only element, or 0 rather is the only number that fulfills this criteria, because negative of 0 is still 0. So essentially, the same logic will also be applicable in this position, because here also we have 6, and in this position also we have 6. So the diagonal elements of a skew-symmetric matrix are always 0, because that is the only way in which we can fulfill this property. Next, let's say we have 1 here. So when we transpose, that element will come here. On the other hand, we have to make sure that this element is negative. So what we do is essentially, we put a -1 here. Why? Say you have been given this position. So let me just highlight this portion for some time. Let's say you have been given this section and you are not aware of this matrix. So you will say, okay, so there's a transpose over the matrix. So these two matrices these two elements don't change position. So I have 0 and 0 over here. This element is the row column wise element of this matrix. So this element goes to this position because I'm changing the rows and columns. So 0, -1 in my final matrix will be 0, 1. But hey, there's a minus in front of the entire matrix. So instead of being 0, -1, it'll become 0, 1. So that is what I get here. Similarly, if I put a 1 here, I should put a -1 here. Let's look at it. So let me just write the solution here. So when we transpose this matrix, we'll get 0, -1, 1, 0. But then there's a minus in front, so this becomes positive and this becomes negative. Doesn't this matrix match with this matrix? So essentially, we have a matrix at our hand whose negative transpose is the same as the matrix itself. This is actually an example for skew-symmetric matrix. The easiest way is to first fill out the diagonals, because those diagonals don't change their position when you change the matrix. Essentially, what happens is you flip the matrix this way. So since I have already been telling it repeatedly that it's rows and columns interchange, so the diagonal does not change. Essentially, if you fold the paper, let's say you have a paper, you have this highlighted paper and you are folding it in this way and you're flipping it this way. So the diagonals don't change their position, and that is what essentially is the reason behind the diagonal matrix, the diagonal elements of skew-symmetric matrix being 0. So that is what we have as the definition of the skew-symmetric matrix.